All right, today we're starting Unit 3, which is exponential functions. Yeah, what worksheet is this going to be? It's going to be worksheet 4. Yes, worksheet 4 when we get started here. Thank you. All right, I changed the little tip on my pen. We're going to see if that helps with its weirdness lately. All right, so we're going to talk about exponential functions, and logs are in this chapter. And I know many of you are frightened. You should have seen this stuff a couple times before, I think. Not the logs, but the exponential part of it, like exponential growth and stuff. But I also know that, the last few years have been less than ideal. So we will go as slow as we need to and revisit stuff. I happen to think this is a fun unit, a new unit for you to finally master some of these concepts. These ideas that we're studying in this unit are called transcendental functions because they cannot be expressed in terms of algebraic operations. They transcend algebra. So exponential log functions are called transcendental functions. I just think it makes us sound brilliant that we study transcendental functions. But anyway, exponential function is anything that is written in the form a times b to the x. Is it not up there? Worksheet 4. Okay. It means x is in the exponent, okay? Exponential function means the x is going to show up in the exponent. All right, so it says an exponential function with base b has the form a times b to the x, where x is any real number and a and b are real number constants such that a can't be 0, b is positive, and not 1. If b is greater than 1, then it is an exponential growth function, okay? So if we had 6 times 3 to the x, yep, my pen's still not working, right? This is a growth function because every time you're multiplying by 3 over and over and over, that's what an exponent means. If you have a b value between 0 and 1, like you had 100 times 1/2 to the x, that is a decay, exponential decay, because you are taking half of it over and over and over. And that decay can be even like 0.98. That would be a 2% loss every time. Does that make sense, guys? You're multiplying by something just less than 1 every time. Okay. The graphs are probably the hardest part for students to get on these. An exponential growth function is when you are talking about like y equals 6 to the x, okay? It is going to be this shape, and it's always going to go through 0, 1. Does everyone understand that any number to the 0 power is 1, right? So it's always going to go through 0, 1, unless there's a stretch. The domain for both of these is all real numbers, growth or decay, all right? The range is positive because you can't take a power of a positive number and make it suddenly be negative. You could do a reflection. So it doesn't ever cross the x-axis. The asymptote is the x-axis. The end behavior on the left or right, depending whether it's a growth or decay, will approach 0, and the other end approaches infinity. Make sense? This growth one is always increasing. The decay one is always decreasing. That sounds like the right words, right? For growth and decay. You are supposed to be able to do this without a calculator. I have many years given a quiz where they couldn't use a calculator on this unit. I'm just not going there this year. I think we have enough on our plates. So you will be able to use a quiz, but you should be able to graph these without a calculator, the idea of them, at least find a few points and know what their shapes are, okay? This is important because later we're going to compare these to log functions, and exponential functions always have a horizontal asymptote, so they're this shape, okay? So this one here is the idea. I guess we'll just do b to the x. If you have an a in front, then it's kind of more like a stretch. Okay. So this one is y equals 2 to the x. So let's just think like 3 or 4 points. So 2 to the 0 would be 1, right? We'll go, you don't have to write this part down if you don't want, but if it's y equals 2 to the x, when we put in a 0, we get out a 1. We put in a 1, 2 to the 1, anybody? 2 to the second, 2 to the third, 2 to the negative 1. That's really important concept. 2 to the negative 1 means 1 over 2. Is everybody with me? Do you remember negative exponents a little bit? That's going to be really important when we get to logs Monday. So that's 1/2. So, okay, real quick, it's over here at 1/2, it's here at 1, it's here at 2, then it goes up to 4, and then it goes up to 8. And it would continue to get really, really tiny as we go more negative, but it would never become negative or 0. 2 to the negative third would be 1/8. That's 0.125. That's pretty tiny on your graph paper. All right, this is a growth. The domain is all real numbers. The range is positive numbers. It cannot touch the x-axis. The y-intercept is 0, 1. The asymptote is the x-axis, which is y equals 0. The entire graph is increasing from left to right and never decreasing. End behavior, as x gets more negative, the y is getting close to what, guys? As we go left, this graph gets close to 0. That makes sense? As we go right, on the other hand, it's just going up forever, so we have infinity. I know I went fast, but does it kind of make sense as you write it? That graph analysis seem okay? Right now, what are you working on? Oh, I don't know. Okay, you're good. All right, y equals 1/2 to the x. If we have powers of 1/2, okay, if we put in a 0, it's still 1. Is everybody with me? If we put in a 1, we'd get a 1/2. If we put in a 2, what would we be down to? I'm sorry. Yeah, if we put in a 2, it would get smaller, right? 1/2 times 1/2 would be down to 1/4. What's going to make this one bigger? If we put in a negative 1, that flips it over, so it becomes positive 2. What if we put in a negative 2? That would flip it over and square it, so we'd be up to 4. Okay, negative 2. Oh my gosh, this graph paper. 4, negative 1, 2, 0, 1, 1/2, 1/4. It's going this way. So that's decay. Domain is the same. Range is still above 0. The y-intercept is still 0, 1. The asymptote is still the x-axis, or y equals 0. But this time, is it increasing or decreasing? As you go left to right, the whole thing is decreasing. And this time on the far left, as you go further left, what's it doing, guys? It's going towards infinity. And as you go further right, it's getting closer and closer to 0. Jada, did you have a question or you're good? Anybody? I know I'm going quick, but I'm hoping it's making sense, so I don't want to spend too much time on these. All right, then we get to talk about a crazy number. Crazy as in irrational. Good? All right, so the number E is not as famous as his friend pi, okay, but he is an irrational number similar to that. Yes?
How are you today?
I'm okay. All right, guys, so this is an important number in math. The definition of it is really exciting. Look, it is the limit of 1 plus 1 over n all to the n as n approaches infinity. Pretty crazy, huh? But if you start putting really big numbers into this weird equation that someone figured out, it gets closer and closer to this number E. So we just need to remember that it's a little over 2, okay? And we need to not be scared when we see an E in these problems. It's just a number. It's called Euler's number. Again, this is just the definition, and fascinating, huh? All right, so E is an irrational number with an approximate value of 2.7, I don't know, do we want more places? 2.718, it's good enough for me. Exponential functions with base E are called natural base exponential functions. And when we get to logarithms, base E will be called a natural log. Does that sound familiar? I think you all would have heard of that before. Many real-world applications of exponential functions use base E, including, we're going to do today, continuous interest. Everybody heard of that phrase, continuous interest? Okay. I think they just want us to put this here, y to e to the x. I'm not going to spend a lot of time on this because it's just like graphing 2 to the x. It says it goes, except it goes up a little faster because it's like 2.7. Okay? So it's this shape. You'd have an ordered pair at 0, 1. You'd have an ordered pair at 1e, which is about 2.7. It's a growth function, and it still has a y-intercept at 0, 1. Everything else, which both of those are even the same, but it's all the same as 2 to the x, okay? It's just going a little bit faster. So don't be scared when you see an E. E. Everybody okay? All right, this is all review. Translations, shifting left. If you had a growth function, like a left shift would be up here. All right. If it went to the right, it might be a 1/3 to the x minus 6. Up or down would be added here. If that was up 7, this would be down 1. Okay. A reflection over the x-axis would be like a negative on a 3 to the x. Would flip it so the shape was this way. A reflection over the y-axis would be a negative in the exponent. Now let's talk about that. If I have a 1/2 with a negative x over here, this really means, Anybody know? The negative flips it over, right? Yeah, it really means the same as 2 to the x. Does that make sense that this flipped across the y becomes this, which we already graphed those? Okay. And then a vertical stretch would be multiplied, like if we put a 4 out here in front, this would stretch it up by 4. So the intercept would move up to 4. And a horizontal stretch or compression goes inside. All right, which I don't think we'll have. So can anybody tell me the two things? This is just over on the side of your paper there, these two quick questions. What are the two things happening to this guy? On the x, a -1 means right 1. Yeah, this pen thing is not helping. And the +1 on the back of the whole thing would be up 1. I don't know why I wrote out the word 1 there. Anyway, what about a negative on the x? That's like a inside negative, okay? And what is an x inside flip? Over the y, yes. That's like this, in case you were, okay? A negative, the other one, a reflection over x, would be this. Does that help some of you see the difference of where the negative would be? Anybody need more time on that one? All right, so here's just a few examples. I'm just going to go through them real fast because you don't have this, but it says 2 to the x plus 1, that would make it move to the left, okay? 2 to the negative x, that's one we just talked about, would reflect it across the y, so it would look like this guy right here in the middle down the bottom. Here's the one that I kind of wanted to talk about just because we didn't do one like this, talk about one, but this is a vertical stretch and a reflection over x, okay? So it's reflected upside down, but also here where it has to go through 1, it's now clear down at -3 because they multiplied it by a 3, or actually -3. All right, so this would be, now you're going to have to do some of this tonight in Delta Math, and you can use a calculator. I'm not going to tell you can't, okay? But this is a 3 to the x that has been shifted which ways, guys? Right 1 and down 4. Okay, so I think I'll use maybe green to do the first one. The normal 3 to the x, just to review, would go through 0, 1. Over here it would be, -1 would be at 1/3. What would 3 to the first power be? 3, yes. And 3 to the second power would be all the way up at 9. 4, 5, 6, 7, 8, 9. Okay. So that's the original 3 to the x. It went through 0, 1. I'll just write the points over here. 0, 1, -1, 1/3, 1, 3, 2, 9. That was a 3 to the x. Okay. What are we supposed to do to all those points? Shift them all. Right 1 and down 4. So where's the asymptote going to go? This was the asymptote. That asymptote, moving it right 1 isn't going to do anything, but down 4. So the asymptote is going to be down at -4. And that's what Delta Math will ask you about. 1, 2, 3. Oh, my eyes just go googledy looking at this graph paper. Okay, so that's the asymptote. It moved down to y equals -4. All right, the point that was at 0, 1 If we move that right 1 and down 4, 1, 2, 3, 4, is now at 1, -3. If we move the point that was at 1, 3, right 1 and down 4, it is at 2, -1. If we move the one that was over at 2, 9, right 1 and down 4, it is at 3, 5, I think. Okay, now I didn't use my calculator. And then this side would just be getting really close to the asymptote. But you can use your calculator, okay? Oh, I was going to show you on here that 2 to the x and e to the x, see it? They're very similar. Remember we talked about how that, and then if you wanted to put in, somebody tell me what this one was again, 3 to the x minus 1. And if you have an older calculator, you have to put that x minus 1 in a parenthesis. If it doesn't put it up in that little box. And then it was a -4. Do I remember that right? Okay, so then you could have gone to the table, which are these numbers way over here, and found some nice ordered pairs. There's only a few of them right there, right? Like those 3. But you will be able to use your calculator. Okay. I don't know if I even want to spend too much time on this. The original 1/2 one would have gone through 0, 1, -1, 2, -2, 4. And this way it would have been down to 1/2. And the asymptote was here, well, at y equals 0 still. What are we supposed to do to this one? Reflect over. Which way are we reflecting when the negative is on the outside? Yep, reflect over x, and then it moved up 2. So the up 2 means the asymptote is going to be up here at y equals 2. So if you take any of those points, you reflect them upside down and then move them up 2. Reflect this down here and then up 2. Down here and up 2. Actually, that one stays where it is, because if you reflect it and then up 2. And this one was up at 4, so it would be down at -4, and then when I go up to here, all right. I would just use my calculator to find some points on that one. Can I just leave it at that? I mean, it's still at 0, 1. If you put in a 1, you'd have -1/2 plus 2. 1 is not a nice one. If you put in a 2, I don't know. Anyway, you don't want to go that direction. You'd have nicer points going that way. All right, part 2 is applications. And I have a reference sheet for you that I forgot to give you. Do you have this across the top of your page on your notes? Okay. On the way out, I'll hand you a reference sheet that has this on it, as well as some other formulas we're going to use in this chapter that you will get to use for that quiz, okay? It's a little half sheet. It's the same salmon color, so you know all the salmon ones can be used on this next quiz. Exponential growth or decay looks like this. You're either adding or subtracting. Where does the 1 come from? Does anybody know if I say something's going to grow by 25%, why do I do that? It's like saying it's 100% of it's going to stay and then another 25% is going to add on. Does that make any sense? And to be a growth function, that number always has to be greater than 1. Otherwise, it's going to get smaller. if something was going to lose 5%, you would say 1 minus 0.05. Is everyone okay with the moving the decimal over twice thing? All right, continuous growth or decay is this formula. It does say K would be negative if it was a decay. Continuous interest is PERT, and that P stands for the principal, or we think of it as the present value. And then E to the R stands for the rate times time. And then compound interest. Does everybody remember doing this one at some point? If you had $100 and your rate was 4% interest and it was compounded monthly, that 4% is divided by 12, but then it's compounded every month, and then if you left it in there 5 years, that's where those numbers go, okay? And it's explained here. Do I need to go over that more slowly, or do you feel like you've used those before? All right. Just in case everybody's good with quarterly means 4 times a year, monthly 12, daily 365. Semi-annually is what they use for twice a year. Continuous interest, again, is that PERT one. That's the only time you use that is if they use the word continuous. All right, and just remember that if it's decay, you're subtracting. So this is the next example I think you have. Is that true? Biology? All right, a researcher estimates the initial population. By the way, that's what goes out in the front. That formula was, did they use P or N sub 0? The initial amount, okay? And then it's 1 plus or minus some rate to the time. So our initial amount is 100. Cells are reproducing at a rate of 25% per week. So is that growing or decaying? Growing. So we're going to do plus. 25% is what decimal? Okay. And it says per week. And then it says how many in 6 weeks. So we don't have to do any converting of units. Be careful on Delta Math. There's 1 or 2 where you have to like change units. But this is just to the 6th power because we're doing 6 weeks. All right, type that in real quick. I don't have a calculator. I'm going to trust you guys. On the home screen, 100 times 1.25 or 1 plus 0.25 all to the 6th. Anybody getting a number for me? This is cells, so we could probably just round to a whole number. In Delta Math, they always specify what they want you to round to. What'd you get, Star? Anybody else getting that? Okay. Any questions? I just suggested that because it's cells and they're so tiny, we just round to a whole number. But in Delta Math, they will always tell you what to round to. So read carefully. All right. Lance has a bank account that will allow him to invest $1,000. So that's his initial investment at a 5% interest rate, which is going to be 0.05. Compounded continuously. What does that mean we're using? That little PERT guy, right? So his present or starting value is $1,000, and then we're going to use this E, which is like 2.71 something, to the RT, and both of those things need to be in the exponent, so it's going to be R is 0.05 for the rate. And what's our time, guys? 10 years, so that's times 10 years, okay? So if I try to type that one in this time on the home screen, was it $1,000? E is, I would prefer you used the E above the LN key. You can use either one, it will work, but if you do second LN, it brings up the little box for you to automatically put the exponent in. So if you get used to using that for E, it will be helpful. And this was 0.05 times 10 goes up in that little box. Again, if you have a really old calculator, you would have to put E. Okay, so 1648.72, if we write that to a penny. 1648.70. Did someone else get that, or did I type something wrong? Okay. If you had an old calculator, I just want to let you know, really old one, you'd have to do, you have to tell it all of that is part of the exponent, okay? Find the balance after 10 years of a $5,000 investment earning 8.5% compounded quarterly. Compounded quarterly is compound interest formula, okay? So the formula is P1 plus R over N to the NT. Did I remember that right? All the letters? Okay, so we have 5,000. Oh my goodness, this pen. 1 plus, how do we change 8.5 to from a percent to a straight decimal? 2 places, so it's 0.085 divided by, what's N if it's quarterly? N equals 4. And then it's to the power of N again times T, because it is being compounded 4 times a year every year. So that would be 4 times 10, or a power of 40. And you could just put in a 40 for the exponent if you wanted. 5,000, parenthesis 1 plus 0.085 divided by 4. And you don't need extra parentheses around that. It will always divide before it adds, so you're okay. To the, and I'm just going to put 40 up there. It's 4 times 10. 11,594.52. Oh, what did I just close? 11,594.52. It might tell you in Delta Math to round to the nearest dollar. I just always do to the nearest cent, because if you went to the bank, that's what they would tell you, right? Questions? Anybody not getting this? Not coming out? I think we might be on worksheet 5, Molly, Mary, sorry. In 2017, it is estimated the United States used about 200 quadrillion thermal units of energy. U.S. energy and consumption increases at a rate of 0.5% annually. We got to move that back 2 more places, so we're talking about 0.005. What amount of energy will the United States use in 2025? I just wanted to do this one because what are we going to have to figure out here? Just how many years it's been, right? So I think that's 8. If we subtract, it's 8 years. Now, it doesn't say continuous interest, so which formula are we using? Does anyone know? Continuous growth. It's just a regular exponential growth, so that would be this one. So we'd have 200. I am definitely not, I'm just going to put quadrillion on the as a label. I don't want to add zeros. 1 plus 0.005 to the 8 years. Now, I left out the plus. Does it matter when you're adding 1 to a decimal? 208.14. Anybody else get in that? And it's quadrillion. I don't know. We could have rounded to whatever they asked us to. Quadrillion thermal units. I'm going to just abbreviate there. This one does ask us to convert units. It says we had 10 rabbits in the field and it's increasing 10% each month, so we'd have 1 plus 0.10, but it's doing it every month, and they want to know this time last year, how many are there now? So how many months if it's a year later? 12? That's all. I just want you to think about the fact that you might have to convert. I'm not even going to finish that one. This is is this the last one I have? Yeah, it really is. This you don't have, okay? But you have this in Delta Math, so I just want to do a quick example. And then if you want to take a picture or something because you're worried about it, you can. It says, Cooper invested $3,100 in an account paying an interest rate of 2.78 compounded quarterly. So that would be 3,100 times 1 plus, this you could do, can someone do, I think it's 2.875, is that right? 7 divided by 8? Okay, so then you'd change it to a decimal. Oh, compounded quarterly, got to do divided by 4, almost forgot. And after 12 years, so this would be 4 times 12 up here. And then it says, Robert invested $3,100 in an account earning 3 1/8 compounded continuously. 1/8 is 0.125. So this is 3.125. And it's continuously, so we need 0.03125 for 12 years. And then it says, how much more money would Robert have than Cooper? So we need to subtract. Now, I think if you subtract in the order that I wrote them, you're going to get a negative number because it was supposed to be Robert minus Cooper. And then it says to the nearest dollar when you're all done. Okay? Any questions about, it's a lot of typing, but I think it'll be okay. Did you want me to finish that one or you got it? You would just do this one, and then subtract them and round to the nearest dollar. And there's not one like this, so I can stop. So the practice is just Delta Math 3.1. I think it's called exponential practice or something. Do we need to talk any more about any of this? Like, you can do this on your calculator if you need to, but this one would be left 3 and down 5. So you would need to, in the Delta Math, I think you would need to say that, you know, the asymptote is down at -5. I'm just going to talk about this real quick. If you went left 3 and down 4 for this function, left 3 would be up there and down 4. Vertically compressed by a factor of 3. Well, if you want it to get vertically smaller by 3, it would be a 1/3. Vertically means out front, and then it says 9 left and up 12. Reflect over x would be out in the front. Translated 1 left and up 6. So there's just a few more examples of how those are written. Are we good? Okay, is anybody totally uncomfortable because I went way too fast? Or does it seem pretty much, as long as you get to use your calculator, it seems